Hello everybody, my name is Dani Colcha and this is my colleague Jefferson Cáceres. We are both engineers in the Escuela Superior Politécnica del Litoral in Ecuador. Our topic of research is in vitro bioactive response of vero-cells on polymethylmethacrylate, craniofacial implants altered with hydroxyapatite and carboxymethyl cellulose. And now my friend is going to give you a brief introduction.
Hello everybody. So let's start by defining what is a craniofacial defect. A craniofacial defect is a modification of the anatomy and morphology of the bone in this area. In Ecuador, 8,726 cases of intracranial trauma were registered only in 2014. As you can see in the chart, the intracranial trauma is the 8th cause of male morbidity in Ecuador. So there are registered 6,232 cases only in 2014. In Ecuador, a very frequent procedure for small size and simple geometry implants is the fabrication of PMMA intraoperative implants. This method has a high infection risk. It's inaccurate and unaesthetic. Also, the PMMA is not bioactive, which limits the implant's materials surgically used, where the ability of implants bone merging is necessary. The aim of this study is to develop a protocol to design and manufacture a PMMA preoperative implants with the aid of 3D printing and silicone rubber mold technique. Manufacturing of bioactive probe of 5 mm diameter and 3 mm diameter thickness were made. Each probe were duplicated 5 times. They were made with PMMA in the form of bone cement. Here we have a chart where we can see the first 3 compositions. The first one contains 40% porosity with CMC gel. The second one 20% porosity, and the third one 10% porosity with 5% of hydroxyapatite. Here we have the second chart of the 2 last compositions. The first one contains 100% of polymethylmethacrylate, and the second one contains only 70% with 30% of hydroxyapatite.
As we can see in this graph, we have 2 axes, and we counted the number of cells per milliliter in each substrate for each day in intervals of 24 hours. In the first 24 hours, we can see that probe A, B, and C are not significantly different than probe D, and this was done with a Tukey HSD test. The only difference we can see here is probe E, that is significantly different than probe E. That may suggest that the substrate has a bioactive behavior. In the first day, we can observe that all of the cell counts are below the maximum cell growth limit imposed by the control substrate. Now 24 hours pass, and we have this other cell count. We can see here that only probe A is not significantly different than probe D, which is 100% polymethylmethacrylate. Here there are 2 main results. The first result is a negative result in the probe B substrate that exhibits cell death and inhibition. In the case of probe C and E, we observe a very high bioactive behavior and proliferation of cells, mainly because of the cell count. But all of this is always under the constraint of the control substrate in this area. In the final days, 72 hours after the cultivation of cells, we observe that probe A and B are not significantly different than probe D. And these probe A and B, as we recall, are the substrate altered with porosity. And probe D is 100% polymethylmethacrylate. The only difference are probe C and E, which exhibit a high bioactive behavior when compared to probe D. What we note here is that probe C and E are not significantly different amongst each other. And of course, they are always constrained by the upper limit, which is a control substrate. These pictures shown in the screen are the optical microscopy images of the surrounding medium around the different substrates. As we can see, A, B, CD, and E, and this is a control substrate, medium. As we can see on probe A and B, this is a medium containing the cells, and we observe a little bit of unidentifiable particles that we assume are dead material. We only observe healthy growth of cells in probe C, D, and E. The main difference we can see here is that probe C, D, and E have very healthy grown vero-cells. But the difference here is that probe C has rich confluency when compared to the other two probes that still have empty spaces between cells. And this is the contour. If we compare the contour to probe C, we see that there's almost no difference, and we cannot tell there is difference. The control substrate is polystyrene. This is a microscopy imaging of the different surfaces in the substrates. We have surface A and B that has a lot of dead material, and also in substrate B. The difference between those is that substrate B has a zone with a lot of large cells. Large cells suggest deterioration and death of the cells in probe B. So we can conclude maybe cells are also dying in both A and B surfaces. If we observe probe C, D, and E, these two have hydroxyapatite, and they have very well-formed vero-cells in the surface, and they are attached. But when we observe probe D, we see that there's a lot of dead material, organic dead material, and there's no attachment of the cells, because these cells that we observe here, the form, the shape, are on the background. They're not really attached to the surface. So what we can maybe conclude from here is that the substrates containing hydroxyapatite are acting as bioactive surfaces because the cells are attached. Whereas in the other substrates, they're not. This picture shows the reconstruction that we did on Blender and with the segmentation in 3D slicer. Here is the corrected defect using the model we created in Blender. After this, we designed a mold in a 3D printed mold. This mold was used to create a model that we then used to create another mold made of rubber, silicone rubber. Okay. Now for the discussion and conclusions regarding implant accuracy. Combined 3D printing and silicone rubber molding techniques are a viable alternative technique for implant design compared to the traditional approaches in Ecuador. These techniques let us create more aesthetic and accurate fitting implants. Also, 3D Slicer, Blender, and Autodesk Inventor software could be used for image cementation, bone reconstruction, and implant design in the future. Now for the discussion and conclusion regarding bioactive behavior. As expected, hydroxyapatite contained in the matrix exhibit a highly bioactive behavior among substrates containing in a C and substrate E, both which contain 5% and 30% hydroxyapatite. Even as little as 5% hydroxyapatite were enough to make the substrate more bioactive. The low cell count in probe A and B may be due to the high porosity in each of the probes. As we recall, it was 40% and 20% porosity, which may have caused to non-polymerized monomer to be trapped in the matrix. This leads us to a conclusion that CMC in those high percentage may not act as a bioactive enhancer because it causes trapped non-polymerized monomer. If we compare probe C to probe A and B, which also had a porosity, the porosity in probe C was so small that maybe the monomer trap wasn't enough to cause death or inhibition of cell growth. Finally, we can say that the inherent porosity in probe D may have caused that the cells couldn't attach to its surface because probe D was 100% polymethylmethacrylate with zero porosity, just inherent porosity of the bone cement. In the future, if implantation were to happen, studies including bone marrow derived mesenchymal stem cells need to be performed in a similar way that vero-cells were used in this study, with the addition of in vivo studies and a deeper examination of the morphology of the porosity of the substrates. Also assessment of cell adhesion and higher magnification, maybe scanning electron microscopy, and also a study in surface roughness and chemical composition of the material. Thank you.